When Yoda just flies
Okay,
around.
so let's give this one more try now. What was that quadratic formula again?
X equals negative b plus or minus square root b squared minus 4ac divided by 2a.
There you go. Never forget. All right, so. Okay, so if we evaluate the quadratic formula here, we're using just this part in here, right? So what do we get? We get x equals one plus or minus
square root
of
negative
minus
4
times 3
times
5 divided by 2 times 3.
Okay. Well, what do you see right away then with this?
You're going to have a negative on this.
Yeah, okay, and so remember, this is the part right here that we call the discriminant in the quadratic formula. It's the discriminant because it's what discriminates between imaginary and real solutions, right? And so you know that if the discriminant is negative, what's going to happen? You're getting two imaginary solutions, right? Two imaginary zeros. What if the discriminant is 0? What's going to happen? That's going to give you 0 under the radical. You're going to get negative b plus or minus 0 on the top. It's the same thing, isn't it? So you're getting one real solution if it's 0, and if it's positive, you're getting two reals, right? Make sense? Okay, so then that's a useful thing. The quadratic formula is a useful place to go, at least initially, because look, you end up with, if you just evaluate the discriminant, even in your head, you can see it's going to be negative, can't you? Because you can see b squared minus 4ac. You can look up there right now and see, oh, that's a negative. So I don't need to factor it. It's not going to factor, right? Does that make sense? Yeah. Okay, there is kind of a good little trick with this, and I'm just going to build in a little good review here for this stuff. What if I give you a different quadratic equation to solve? Like, how about something like, what if I gave you, let's say we had the expression something like that, and we want to factor it. Okay, how could we, actually, let me think about one. Let me see here, what if we do like, so,
I'm gonna have nightmares.
yeah.
Of a baby
That
dancing.
baby dancing?
That was in a cage and he's just birthed and then he started dancing.
Wait, can we record all of us singing?
Play.
Sure.
I think
Yeah.
he's already been recording. So. Oh, are you talking
Oh,
about like?
yeah, I recorded it. No, I recorded it.
Ice Cube.
Oh, you recorded?
Ice Cube knows.
Yeah, we can just look
We
at
all
the video.
just need to go find a distance one.
Ice Cube knows the quadratic formula.
So does Yoda.
So does Shakira.
So does Yoda.
Okay, let's factor this one. Okay, and we could use, so the suggestion of the quadratic formula, there is a way to do this, right? There is a way, I'm hoping this is what you're getting at, but if it's not, I want to show you. So there's nothing there's no greatest common factor there, right?
Correct.
But we could use the quadratic formula. We could, by the quadratic formula, we're going to get x equals, like if I'm setting this equal to 0, let's say, we're trying to solve this equation, right? Okay, or even if we're not, we just want to factor it. So I get x equals 11 plus or minus the square root of 121 minus 4 times 15 is what, 60? So we're going to get a plus, aren't we? 60 times 56 is going to be 3,360, is that right? Divided by 30?
Thank you.
Okay. Right, isn't that right? Should be. Yeah, that's right. Okay, okay, so now what? We simplify, right? So we're gonna get 11 plus or minus the square root of, what's that gonna be, 3481?
Yeah.
All divided by 30. Okay, so we need to simplify that radical. Okay, remember, so this is good practice. How do we simplify that radical?
Break it down.
Okay, so I wanna factor it maybe, right? Because I wanna find out, what I'm really trying to find is, I'm trying to figure out what's the greatest perfect square factor of 3489. What's that? I want it, say it again?
50.
Oh, okay, so it does work out to be a perfect square, okay? Okay, so it's 59, and do you see how we couldn't do that though? Everybody, you guys know, the couples go out, singles stay in trick?
Yeah.
Okay, good, so we're good, all right. So then we end up with 11 plus or minus 59 over 30. So if we take the plus, we're gonna get 70 over 30, which is 7/3, right? If we take the minus, we're gonna get negative 48/30, which is, what's that gonna be? We're gonna get, 8/3. Is that right?
Wait.
No, that's not quite right.
24/15.
It's negative 8/5.
Negative 8/5. there it is,
Yeah. Okay. All right, so how can we, and this is fair game, how can we turn those into factors?
You will set each of the factors.
Yeah,
Zero.
Okay, right, so here's the piece, what does it mean if they're factors, right? If they're factors, what we're doing is we're trying to, why are factors useful? Factors are useful because we want to be able to apply the zero product property, right? That's the whole point of factoring. If we've got an equation in standard form where it's set equal to 0, we want to be able to break this into factors and set it equal to 0 so we can apply the zero product property and set each factor equal to 0 to find the zeros, right? Okay, we're just kind of reverse engineering this, aren't we, right?
Yeah.
We're working backwards up to the point where we want to, till we get to the factors. We know what the solutions are. They're 7/3 and negative 8/5, right? So how do I take that and reverse engineer it up to this point? If I'm starting here, working backwards from the point where I have, for example, x equals 7/3, what can I do?
X minus.
Okay, so here's the relationship. X minus the 0 equals 0, right?
Correct.
Okay, and now that's awkward, right? We've got a fraction in there, but I could easily clear the fractions by multiplying both sides by 3. Aha, if I multiply both sides by 3, I'm gonna get 3x minus 7 equals 0, right? Okay. And then I could do the same thing over here with my negative 8/5. If x equals negative 8/5, then that's the same as saying x plus 8/5 equals 0, right? Which is the same as saying 5x plus 8 equals 0. There you go. Right. Okay. So that's kind of a cool little trick you can do with the factor. If you got something really hard to factor, I mean, even if you wanted to write something that's not factorable to the point where you're going to have, like, let's say, rational coefficients. And what if you even wanted to have factors that involve square roots? You can always do this, right? You can always find, you can even find irrational zeros with the quadratic formula and then just work backwards to write those in factor form if you want to, right? Okay, so there's one way to do it. Okay, what if we want to factor this more directly? Can't remember, maybe we've talked a little bit about this, I can't remember, but you'll tell me. How could we do this more directly? Factor this. We could cheat, use quadratic formula. But how do you deal with factoring quadratics where 8 is not equal to 1? A is 1, it's easy.
Well, you times
A times
C.
So you're trying to find numbers that multiply to to A times C.
Yeah.
And add to
B.
B, okay. So let's find those, right? So we gotta find, in Algebra 2, I always call those magic numbers, right? We gotta find magic numbers that multiply to AC, which is gonna be, what's that gonna be, 5, we'll multiply to negative 560 plus 280, so what is that? Like 840? Multiply to negative 840 and add to negative 11, right? Right. Finding those numbers is not terribly easy, but what are my approaches there? I could try to find factors of A times C, and that's fine, right? We can do that. We can take that approach where we're gonna do like, let's start with, I just wanna show you a couple patterns here. And stop me if I'm doing stuff that's just too obvious and it's not worth talking about. There's some things that I always go through and I didn't have you guys, so I wanna make sure that this is all stuff that you're comfortable with. So when we make our factors of negative 840, we can start off with really disproportionate ones, right? So we could have something, we know that we want to add to a negative, so the negative's going to have to be a little bit bigger, agreed? Okay, so we can start with negative 840 times positive 1, and let's just keep track of the sum over here. Well, that's a huge sum, negative 839, way too big, right? What next? We're not going to do all of these, but
Can we just do like 84?
I could do negative 420 times 2, and then I'm getting smaller sums, right? So negative 418. But what do you notice? There's an important pattern here. As the factors get closer together, what's happening to the size of the sum?
Decrease.
It's getting smaller, isn't it? Right? And that's an important thing to remember when you're looking for factors. I'm going to get really big sums when I've got disproportionate factors that are very far apart, and as they get closer together, the minimum sum I'm going to get is when I get the two closest factors I can get. Agreed? So we could probably skip down this list a little bit, couldn't we? Like we could skip down to something like negative 84 times 10, and we're getting closer, but we're still quite a ways off, aren't we? Right. But as long as these are both even, I know in this case, like I could cut that one in half and double that one, right?
Yeah.
Okay, and in fact, I could even maybe cut that one by a factor of 4, because 4 goes into that. So we can skip down a little bit more and do negative 21 and positive 40. Oops, that's too much, isn't it?
Yeah.
Went too far. Okay, so we gotta go back a little bit. So we could do negative 42 and positive 20. Okay, and what was that at to? So
Negative 20.
negative 22, so we're getting closer. Well, what do we probably have to do then there? We probably needed to divide by like 3 or something, right?
Yeah.
See what I'm saying?
Yeah.
So then this one would become, what if I divide that by 3, I'm gonna get 28. Yep. Negative 28, and this one's gonna become 30. What the heck?
Negative 35.
35 and 24, is that what we need? 35 and 24, okay. There we go. Okay, so there we go, that's the one we want. Negative 35, positive 24, and that works? Okay, so that adds up to, that's what we need, right? That gives us our negative 11. Okay, my point is, that's kind of hard to do, right? I mean, it's a time-consuming process. When you got really big numbers like this, and especially when the sum is negative, what does that mean? If the sum is negative 11, what's that telling you about the positive and the negative numbers?
The larger number's going to be negative.
The larger number, and how much bigger is the larger number?
By 11.
11, right? So what might be an easier approach to finding the magic numbers here? I mean, wouldn't it always be easier to just make a short list of numbers that differ by 11? And then just hone in on the one that's going to give us, if it exists, the one that's going to give us the right
You see what I'm saying?
Yeah.
I mean, we could pretty easily, like, we could get pretty close to this, couldn't we? We could say something like, what if we said, like 40, like we could just try a couple, right? Like 40 times 29 is gonna be too big. Agreed? 30 times 19 is gonna be too small. So we know it's gonna be somewhere in the middle. So what if we just arbitrarily pick something down here like, what's our number again, negative 840? So what if we pick something like, what if we just said arbitrarily negative 33 and positive, what, 22? That's an easy one to do. What are we gonna get for our product this time? Right, this time we're trying to do a product. So what's that gonna give me? I'm just gonna get,
Negative 726.
negative 726. So we're not quite big enough, right? We gotta get a little bit bigger. Let's skip, and we'd pretty easily get to the right one then, wouldn't we?
Yeah.
Right, you see my point? So that's gonna get us to this point pretty easily. Okay, once we get the numbers, what are we gonna do with those? How do you factor it once I have the magic numbers? Well, how did you guys learn
You did the bottoms up.
it? You did bottoms up? Is that what you did?
I don't fit to remember.
I'm just curious what you, I mean, there's multiple ways to do this.
So then you-
So what would I write there?
13x minus 35, or 15x, sorry, 15x minus
15x minus
35.
35
Times 15x.
a quantity
Yeah,
times,
probably 15x minus, or plus 24.
And then you just.
Yeah.
what was it, plus 24?
Yeah.
What if you did the way around?
So you guys are doing,
Yeah,
so
it
you
would
are
be-
doing bottoms up, right?
Kind of, and then you just take out the common factor.
Yeah.
Then you, okay, so then you would have factored out,
Like a 5.
Like a
in the
5,
first one,
okay.
And then a 3.
so then you're left with 3x minus 7,
Yeah.
and over here, you take out a 3, right?
Yeah.
And you're left with 5x plus 8.
Yeah.
Okay. Then what do you do with the 3 and the 5?
Yeah, put them over to the 2.
You just divide everything by that? Okay, so you're kind of doing a modified bottoms up. Okay, that's fine. That's, okay. That's okay, I mean, that's okay to do, yeah. I'll show you one other way to do this, it's kind of, that's kind of interesting, because it dovetails really well with what you do with polynomials. You could do this one by factoring by grouping, okay? Because that's something you do a lot with other higher order polynomials. So all you'd have to do with that one is we're gonna take this, we're gonna break this, when you factor by grouping, remember factoring by grouping?
Yeah.
Vaguely, it's probably good to go through some of this stuff. So you have to have an even number of terms to factor by grouping. So we're just gonna split that middle term into a sum. And what's the sum gonna be? Well, it's based on the magic numbers. So we're gonna do 15x minus 15x squared minus 35x plus 24x minus 56. And the order makes no difference. You can do it either way, it makes no difference, right? And now that we've got 4 terms, we can just factor this thing by grouping, right?
Yeah.
And that's where we're gonna factor out, so it's gonna look very similar to what you guys did. We're gonna factor out the greatest common factor here, which is gonna be 5x, leaving us with 3x minus 7, okay? And then we've got this plus sign in the middle, right? So we won't do that, well, plus, I just want to keep track of that, so that's our plus sign. And then remember, when you factor by grouping, you have to have the same leftover factor in both groups, right? So you know for this to work, you have to end up with a 3x minus 7 there. So you just ask yourself, well, what would have to go there for that to happen? Positive 8? Okay, and so now look what you get. If you factor out a 3x plus 7 from each group, what's left behind? 5x plus 8, right? Okay,
That's, oh, okay, that makes sense.
see what I'm saying?
That's why grouping works like
Okay, and then if you, right, so if you do that, then it's, the nice thing about it is it's algebraically correct the whole way through. You're not taking, like when you do factor by grouping, you're actually writing a couple things down that aren't algebraically correct. You're just kind of, you know, I mean, it works.
Anyway, okay, so probably enough factoring practice. How about this one? Let's factor this guy.
Yeah, take that.
Okay, good, so we can, good, and that's the point, we can take out an x minus 2. And what's left behind if we do that?
7 minus 14, or,
Minus
yeah,
three.
that works too.
Okay. And if we wanted to simplify this then, we could, we could distribute and simplify inside the brackets and get 7x minus 14 minus 3. Everybody agree?
Yeah.
Okay, good. How about this one? It's a little odd. Probably haven't seen one like that before.
No.
But you can do this. What do you think I want to, suggestions?
There's the next one.
If you make the, yeah, you
But-
can take that and take that.
Say it
But-
again. What are you gonna say?
By 2 if you get rid of fractions.
So when you say that again,
Multiply by 2 if you get rid of fractions.
meaning get a common denominator, is that what you're suggesting?
Yeah.
Okay, because I can't just arbitrarily multiply by something, or I'm gonna change the expression,
Well,
right?
Oh, well, we just have an expression there.
But the
Is it
suggestion
equal?
is, I think that's what you're saying, it's a good suggestion, we could get a common denominator here, right? Which might be helpful, okay? Another way to look at that is, I could factor out a 1/6. Okay?
Yeah.
That make sense? How come? Now, this is kind of an odd way of going about this because there's no context in this problem at all. But where we're getting with this is, when we do derivatives, we're gonna get some really strange looking results like this, and we wanna make them manageable. We wanna get them into a form where we can do something with them. Keep in mind, kind of keep a lens looking forward in the class. What do you think we're gonna do with derivatives? I mean, right now, we're just practicing, calculating derivatives, but we're doing it for a reason. At some point, and I'll give you just a little bit of insight, I think I've even mentioned this before, but at some point, we're gonna wanna use those derivatives to find interesting places on functions. And some of the most interesting places are where we have horizontal tangent lines, which is where the derivative equals 0, right? And a lot of times, we'll also wanna find places where the derivative is undefined. And so we need to know if we're able to factor the numerator and factor the denominator of some ugly rational function that we get when we take a derivative. Then we can look for places where the denominator is undefined, but the numerator is defined, right? And that would mean those are places, interesting places to us also. That's a lot of talking, and if that doesn't make total sense, it's okay, we're gonna get there. But the point is, we wanna be able to factor this stuff, right? We gotta put this into some kind of form where we can see the factors, and we need to factor it in some way, right? So it'd be nice for us to be able to do a couple things. We want to always consolidate this into a big rational function where we get some stuff on the top that's organized and some stuff on the bottom that's organized, right? So one thing we could do is we could factor out the least common multiple of all the denominators, aka the least common denominator would be a 6, wouldn't it? So let's just do that step first. If I factor out a 1/6, I want you just to think about what that means. Factoring means I'm dividing away a 1/6. Everybody agree? Okay, so when I factor out a 1/6, it's the very same thing as dividing each term by 1/6. Okay, this is what's left over. Dividing by 1/6 is the same thing as multiplying by 6, right? So if I want to take a 1/6 out front, and I want to figure out what's left behind, how do I make that connection? Well, what's going to be there?
8.
Yeah, everybody see that? Yeah. That's just gonna be an 18x squared. What's gonna be there?
3x.
3x. Everybody agree?
Yeah.
Because if I'm factoring out a 1/6, that means I'm dividing each of these terms by 1/6 to see what's left behind, which is multiplying by 6. Good. And then right here,
2x.
okay, 2x to the -1. So that's good, right? That's nice, because then at this point, look what I can do. I can write this on the top. I've got stuff on the top. And stuff on the bottom. That looks better, right? Okay, but what about the x's? There's something goofy going on with these x's too.
What do you want?
I
I've got this x to the minus 1.
You want to put that on the bottom.
Okay, so, right, so now, we'd like to not have a negative exponent in the top, because if I were to write that as a fraction, it means I've got a fraction in the top of my fraction. We don't want complex fractions, right? So what are our options? Well, I could just trade this thing right here. I could trade this for a 2 over x, and we've done stuff like this already. I could get a common denominator on the top, and then flip and multiply by the bottom. Everybody agree? So I'd have to multiply each of these by x over x to get a common denominator. That's going to work. It'd be fine to do that. But there's an easier, more effective way of doing this. We're just going to factor out the least power of x. Okay, what's the least power of x in this polynomial? Negative 1, right?
Yeah.
We can do that. If we factor out an x to the negative 1, what are we left with? Well, we're left with whatever we get when we use that simple quotient rule, right? If we, when we divide by a power of x, we just subtract. Does that make sense?
Yeah.
Okay, so let's do that for our second step. Second step, and we could probably combine both of these next time, right? So we're going to get an x to the minus 1 over 6 times what's left behind. Well, if I factor out an x to the negative 1, what would I get here? 18x cubed. Good. Right? Make sense?
Yeah.
Okay, what do I get here?
3x squared.
And what do I get here? Okay, makes sense? And once again, how do I make this connection? If I'm factoring out an x to the minus 1, it means I'm dividing by x to the minus 1, right? Dividing by x to the minus 1 means I'm going to do this exponent minus a negative 1. That's plus 1, right? Everybody get that?
Yeah.
Okay, and then I could write the x to the minus 1 as an x on the bottom. And so all that means then is I'm going to get 18x cubed minus 3x squared plus 2 over 6x. Now that's a lot better, isn't it? Right? Now we can do something with this. Now we could go up here and we could find the zeros of the top relatively easily, if we wanted to, right? Even if we did it graphically. I could find the zeros of the bottom. What's the zero of the bottom? 0. Is 0 a 0 of the top? No. So then we found something interesting already. We know that this function is undefined at x equals 0. Okay? If this were a derivative, that would be an important thing to know in the future, right? Okay? So let's practice this a little bit. I bet you we can even, let's try one more of these just for practice. There's a lot of just algebra practice.
Just help me through this.
You can take out,
X squared
Okay, I could take out,
An x squared minus 1, yeah.
1.
okay, I could take out an x squared minus 1 to the,
1/4.
no,
3, negative 3.
that's the least power of that base, right? What are the things I can factor out? If I'm factoring out, like I can factor out things that have common bases from these two factors, right?
Yeah.
Like I've got x to some power here, I've got x to some power there, right? So I can take out, let's just kind of look at this in an organized way here. What's the stuff that we're going to have out front? Well, for this particular base, and we'll kind of color code this, for the x's, I can only take out an x cubed, the least power of the common base. So I can factor out an x cubed, which is going to leave me behind with what? I mean, over here, I'm just going to get it, that's going to go away, right?
You
Yeah.
can also take out the 5.
I'm going to get an x squared from this guy, right? Okay, I could take out, what about the numbers?
Yeah, you could take
I
out
could
the
factor
5
out
over
a
2.
5, in fact, let's factor out a 5 and let's factor out a 1/2, right?
Yeah.
We don't have a fraction.
8.
Okay, so if we take out a 5/2, what's that going to leave us with? What's that going to leave us with in the first term?
8.
Okay, I'm multiplying by 2/5 to find out what's left over, right? So I'm going to get 20 times 2/5 is 8. And then what about over here? I'm just going to get a 1 on this part. Agreed?
Yeah.
Okay. What about the other like base that we have? The x squared minus 1. Well, the least power of that base is the negative 3/4.
So what's that gonna leave us with? Well, here it's gonna leave us with x squared minus 1 to the 1/4 minus negative 3/4, which is 1.
Yeah.
Okay? And then I get my plus, and then all that's left over here is just gonna be my x squared, right? Everything else factored away. Right? And so if I wanted to write this then as a rational function, we're just gonna have a bunch of top stuff and a bunch of bottom stuff. Well, what gets stuck on top? I got 5x cubed. That's gonna go to the bottom, isn't it?
Yeah.
Right? And then I'm left with inside here, this stuff, which I could simplify. If I distribute the 8, I'm gonna get 8x squared minus 8 plus x squared.
9x squared.
Okay, and on the bottom, we're gonna get my 2, and we're gonna get an x squared minus 1 to the 3/4. Okay? You might be thinking, oh, mister, you're not supposed to do that. You're not supposed to have a radical on the bottom. We don't really care. That's just, we don't do that.
Elementary school life.
Okay, make sense? All right, so let's try this. Let's try a couple things.
Sorry.
Let's actually differentiate this, just a product rule, but this is different than the old time product rules we used to do, because look, one of the factors in the product rule is gonna require chain rule to differentiate, right? Now, we could, what are our options here? I mean, is this the only way to do it? No, I mean, I could just expand this out and distribute the x cubed, and that might even be the easiest way to do this one. Because then I'm just gonna get a simple polynomial I can just differentiate term by term, right?
Yeah.
Okay, but let's do it this way, just to kind of establish how we do this. Sometimes, because like in this example, we don't have that option. We have to use product rule there.
Yeah.
Okay, so we're kind of warming up to that a little bit. All right, so f prime. Help me out with my product rule here. I'm gonna get what?
Well, you're gonna
X cubed times
times,
the derivative of that.
yeah.
Okay, now that's a chain rule issue, right? So what's the outside layer there?
The 2 squared.
Okay, I got hand squared. What's the derivative of hand squared?
2 hand
2 hand to the 1, good.
Yeah.
Times the derivative of what's inside, well, that turns out that's a 3x minus 1. So what's the next link in the chain?
3x.
Okay, 2 links in the chain because there's 2 layers to the function, right? Plus, now we'll flip it around, we get 3x minus 1 squared times, that's an easy one, it's a 1 layer derivative.
3x squared.
Okay, good, so, well, we could maybe clean this up just a little bit. So we're gonna get 2 times 3 is 6x cubed times 3x minus 1 plus 3x squared times 3x minus 1 squared, quantity squared. Okay, I mean, once again, we could just easily distribute and combine like terms, but let's go ahead and take advantage of the fact that we can't factor this a little bit.
Yes.
Right. So what have we got here? What about the numbers? What can I factor out of the numbers?
3.
3, okay, so we can take a 3 out from the numbers. What can I take out from, I got some other like bases. I've got
Yeah,
x's here.
x squared.
So I can take out an x squared, and what about this other like base?
3x
squared.
3x minus 1, and that's gonna leave us with what behind it? So I'm gonna get a
2x.
2, I'm gonna get an x, and that's gonna go away, right? Plus, here I'm gonna get, those go away, and I just get a 3x minus 1. And so there are some advantages to this, right? It's factored now, isn't it? Okay, so we end up with a final answer. We've got 3x squared times 3x minus 1. If I simplify this, I just get 5x minus 1. And it's factored for me. My derivative is factored. Okay?
Yeah.
Let's try this one. So what about that 1/2? What are my options with the 1/2?
You can just make it hang on to the x.
I could, so I could group the 1/2 with the x if I want to, right? And I could think of this as being x squared, or x to the 7th over 2 times this radical if I want to, okay? That's perfectly fine. What's another option? When I differentiate a constant times something, what did I do with the constant? Like, just in general, what's the derivative, when are we out of here? 1 minute? 1 minute, okay, well, yeah. Well, this is where we'll leave off, but for now, what's the derivative of, with respect to x, of c times f of x?
C of F
Yeah, c times f prime of x. That may not seem like much, but that's pretty important. That constant just stays out front, doesn't it?
Yeah.
So one other option we have is, let's just pull that 1/2 out front and forget about it, right? Let's just leave the 1/2 out there. And then we can distribute the 1/2 through, but let's just look at the product of the stuff in the yellow brackets, right?
Yeah.
Okay, we'll end it there.